Today, I was hoping to have a guest speaker, but it is NIPS is approaching, the main conference of this field. So most guest speakers are like, I would love to come, but my paper deadline is killing me. So on the plus side, that means I will give you an overview. Instead of hearing one person talk about one project, I will give you an overview of a handful of other interesting deep learning NLP projects that cover a broad range. And before we do that, I'll just give you, again, a model overview that allows you to properly compare existing papers and also hopefully try to do a better job than most existing papers out there in comparing to previous work. And then we can actually have some fun. Basically, try and apply the various techniques and models that we've learned in the class to a bunch of different problems, so you can see all the possible applications, or well, at least a small subset of the possible applications that you could, in theory, now implement yourself. So let's start with the model overview. There are basically four parts to this: the word representations, how do we compose from the word vectors the phrase computations, the objective function, and the optimization. And there will be a couple of things in there that we haven't discussed much, and that if you're really interested in that area, you can probably, or you should look up yourself. So on the word vector decision space, you can essentially just randomly initialize your word vectors and just have them trained with the model that you actually care about. So maybe you train a sentiment classifier, you have a very large sentiment data set. You do have that option of just randomly initializing them. And then there's word2vec and there's glove. And I sort of highlight in bold here what I think is currently the best model in each of these different regions. I do think glove is the best model. Unless you want to train your word vector sort of in an online fashion, you don't want to first collect all your statistics, your concurrent statistics over the entire data set, but you want to train it sort of one window at a time as new windows come in, then you'd still want to use word2vec. Yeah?
I'm going to say, just for interest's sake, there's also a recent paper out of Princeton's group with Sanjeev Arora, where they kind of give a generative model that underlies something that's basically just glove. So it's kind of interesting if you like statistics that there's further, more analysis of what the actual underlying assumptions, or what a generative model that gives you something that's almost exactly like glove is.
Yeah.
That's
Yeah.
nice too.
It's true. So it's just a comment for the people in the video who couldn't hear you. Basically, Sanjeev Arora from Princeton University has actually, I think, some of the most interesting theoretical work on deep learning. So if you're interested in more interesting theory and mathematical sort of underpinnings of these models, check out Sanjeev's work from Princeton. He has both work on autoencoders as well as now word vectors. One thing that's very important for you in your comparisons is if you say, oh, my model is better, and then you find that using the latest and best word vectors that weren't available in the previous paper really give you that extra 2 or 3% boost over that previous paper, then you in a perfect world would actually plug those new word vectors into the old model and see if it's actually your model that improved or if it's just the word vectors that gave you that boost. The number one decision that you'll have to make once you decided which kind of word vector you want to use is also the dimension. So that basically, in many cases, defines sort of the number of model parameters downstream. One thing we'll actually cover today is that instead of using word vectors, you could also just directly work on the character level, or even go down to the morpheme level, which is interesting, more so than it's been shown to be incredibly useful. Just put it like that. All right, so now phrase vector computation. We have your word vectors. Usually we don't care about just classifying a single word without a context, right? And so we basically looked at a bunch of different composition functions which govern how exactly the word and phrase vectors interact to compose the meaning, or in our case, the meaning vector of the longer phrase. And one thing we haven't really discussed that much, but is actually also a useful alternative you should know about, is just averaging. I think I mentioned it to a lot of you in the project advice office hours. Just simply averaging and putting a deep neural network on top is a useful baseline. You can very quickly implement it using your first problem set's code and just average a bunch of word vectors. There are actually lots of simple alternatives that you can also do. You can have weighted averaging and so on, which I'll go over in the next slide. And then this is just the overview. So there are basically a lot of related models that in some ways boil down to be special cases of the matrix vector RNN that I mentioned in one of the talks. So in the matrix vector RNN, we basically computed a parent vector based on the two child vectors, and each word is represented as both a vector here in small letters and a capitalized matrix. And in order to compute the parent vector, you'd apply the matrix of one word to the vector of the other and vice versa, and then you still had your standard W matrix of parameters of a single neural network. Now, it turns out there's actually a bunch of work in traditional NLP that boils down to be a special case of these kinds of models, where instead of having a nonlinearity, you just have the identity function here. So you have not a neural network, just a linear layer. And in some cases, the models ignore having the W here, so you just have two identity block matrices. There's one paper which is kind of funny in retrospect in some ways, because they basically say A is always an adjective matrix and B is a noun vector. So they say every adjective is represented as only a single matrix, and every noun is only represented as a single vector. And they showed some experiments, but if you think critically about this, you'll realize very quickly that nouns can modify other nouns as well. You don't always just want to have an adjective modify a noun. You may have something like a disk drive, right? And now you want disk to modify what kind of drive you have. So this was just a very specialized model in natural language processing for this, particular types of bigrams of adjectives plus nouns. And then we covered a lot of these different recursive neural networks that I've worked on in my PhD. I think of all these various options, the recursive neural tensor network, if you want to be in the recursive space and actually have grammatical structures and find phrases, the RNTN is probably the best default model to try. Yes?
This is specifically for vector compositions though, right?
That is correct.
You could also do something like compose similarity functions instead. Like I think Turney does some work on that.
Mm-hmm. That's right.
So
Yep.
What do you think about the trade-offs between the two?
Between,
Like just like straight up composing vectors and maybe making well, first of all, you either come back to a vector or you have to like make some kind of matrix, right?
Mhm.
Which if you do a matrix, it gets a lot larger as the vocabulary size grows. So. And then there's also similarity, which is less like memory intensive. But like, do you think the work in similarity function composition is like?
so in some sense, these are also functions that compute similarities, right? And in many ways, the evaluation that we do on top of the vectors is just evaluate how similar, how much do they correlate with human judgments and so on. So these are all similarity learning functions. And it's just that it happens to be that there are a lot of very simple alternatives. So the simplest one, if you just wanted to have averaging, right, is also a special case in some sense of this function, though it is becoming somewhat of a silly game where you just have identity matrices all over the place in the identity function, or you have and times 1/2, right? And then that is the simplest way to compute the vector average and staying in this kind of framework. So I don't know if that answers your question, but these are all ways to compute functions. You can then also say, oh, I want to take TF-IDF weights and multiply the identity matrix here with the IDF weights so that you can add. It's always easy to add human knowledge into your models, right? You say, oh, I don't care about and I already know I don't care about that because it has a very low inverse document frequency in general. So I just multiply these terms with that. The beauty of deep learning is ideally if you have enough data, you don't have to do any of these things. Then if you are inside the recursive space, you also have the choice actually of tree structures. We covered mostly constituency trees, and today we'll bring back again a little bit the dependency tree. It's basically a very similar kind of idea. You just recursively combine things, and every time you have an arrow that you see here, you basically have a neural network layer. It's just the main difference will be that you have multiple possible children, but you'll just sum up what they are and have here multiple blocks in the row and multiple elements for each child in the column. What we haven't really discovered or covered much are balance trees. So instead of having to use a parser, you don't necessarily have to do that. And in some ways, people say, oh, recursive neural networks aren't great because now I need to run this external parser. Well, you basically can separate a lot of these design decisions, right? You can still use recursive neural networks and not require a parser by just using a balanced tree. And then it becomes more similar again to a convolutional neural network, just without pooling. But pooling can also be an operator that you use inside a tree structure, right? So the main goal here that I have is to try to not have you become very religious about, oh, it has to be this model and so on, because they're actually very smooth interpolations between the various different model families. We covered convolutional neural networks and looked at a couple of variants. You don't have to have a pooling layer. You could just combine matrices. There are lots of different potential pooling layers, and you can also pool across different dimensions. There's one good question. You can pool across the different dimensions of the word vectors or across different time steps and so on. They are still somewhat less explored in natural language processing than either the recursive or the recurrent neural networks. And I think that is largely because they're neither linguistically nor cognitively very plausible kinds of models, but that doesn't mean you couldn't get good performance with them. Especially if you want to work on GPUs and very fast implementations, they're probably very useful. The last one, I think, is for reason. Basically, using recurrent neural networks is personally where I think the most interesting future research lies, and especially when you use the ideas of gates. So gated recurrent units or long short-term memories are, I think, the way to go. But again, this will be up for debate. It's still an active research area. There are a ton of different variants of LSTMs, so if you're interested in this, there's a great paper that just recently came out a couple weeks ago on LSTM, the Search Space Odyssey by Grave et al. Definitely a good paper to explore if you're into that. And then the third choice for your models, and again, these are also useful for you if you're stuck in your project and you want to analyze a couple of more options of how to improve your performance, then these are great things to try. So you can have the max margin loss that we talked about. You can also use cross entropy error for the standard softmax. We also can have autoencoders, which we don't cover very much, or I didn't cover very much in the class, largely because I think the benefits are somewhat unclear in natural language processing for them. What is an autoencoder? It's essentially a very simple neural network function. And in our case, you could think of it as it returns, it's given as input 2 vectors. It maps it to 1 vector and then tries to recover these 2 vectors. And you would think this vector now is a good vector because you're able to recover the original input. So the objective function here is just you have child 1, child 2, child 1 prime, the recovered one, and child 2 prime, and you're trying to minimize C1 prime, C2 prime as a vector minus C1, C2, the original one. So all this we'll learn is basically the identity function. But the identity function where you have an informational bottleneck. You have here a 2n-dimensional vector, you map it to an n-dimensional vector, and you try to recover a 2n-dimensional vector. So if that function was perfect, then really this one vector would capture all the information that was in the 2. And I thought for a while also this is a very useful way to represent language or to learn compositional kinds of vector representations. But in the end, I realized it's not necessarily true. It's being able to fully recover that doesn't necessarily correlate well with human judgments of similarity, for instance. So that's part of the main reason why I haven't really talked about this model family very much in the course of this class. Some people say, well, but let's not knock out this objective in general. But then once you dig in, a lot of times they don't actually want to auto-encode. They don't want to encode the vectors themselves, but they want to encode something else. And so where this is really interesting is if the encoder becomes another language. So we covered, for instance, the LSTM to LSTM translation model. But then it's not an autoencoder anymore. It's an encoder and a decoder in a different modality. And at the end of this class, we'll actually cover encoding images and then decoding them into language. So having sentence descriptions of images. And there's lots of interesting work in that. All right, and the fourth option that you can and should explore in the next 2 weeks for the final stretch of your project is also the various different tricks on optimization. So we covered a couple of important initialization tips and tricks, especially important for the word vectors and the composition parameters. And then there are a bunch of different optimization algorithms. We only covered a couple. If you're interested in this space, you definitely want to try SGD and momentum, which is in many cases a good default to do in AdaGrad if you have word vectors that you're also learning. We also covered the optimization tricks of regularization and dropout, especially if you have very large models, you do want to use dropout. Okay, so now assuming you have a good grasp of the various design decisions that you can make in your project, let's look at a couple of fun applications of deep learning to NLP that we haven't covered, largely because they're a little more complex, sometimes not quite as well established, but also in some cases fun, but not necessarily leading to great performance on real NLP tasks. The first one of the 4 or 5 applications we'll cover today are character recursive neural networks, which in some ways are amazing, but in other ways still lack compared to using word vectors and words as sort of our most atomic kind of representation. So what are RNNs on characters? Basically, you just have, for any string of characters, such as here hello for instance, you just at every node try to predict the next character. That's all you do. And you can use here a standard recurrent neural network, but really in most cases people use LSTMs for these because then you have a nicer memory and you can keep track of things. And like I said, there are really interesting results here that you can get when you train on these and then you sample from the model afterwards. You say, all right, imagining the model being able to predict whatever it wants. You just sample randomly from the softmax that you predict at every time step what character it would be, what kind of sequence would come out. So here are a couple of interesting results from Andrej Karpathy's blog. He actually just re-implemented these kinds of ideas last week, or maybe earlier this week, and showed a couple of interesting examples. So imagine you train your character recurrent neural network with LSTM kinds of units on Shakespeare, and then you just sample randomly from the model. Again, you just have our standard RNN that we covered in the class. You have a softmax at every node. The softmax goes over all the English characters, including capitalized versions of them, and then you sample as you go. And what's fun and interesting here is that they really, from afar, look like it's real. But then once you look closer, you really, it still makes some misspellings, but it basically doesn't make any semantic sense. It sort of sometimes makes local syntactic sense. And so this is from Shakespeare, and again, the earth and thoughts of many states, it doesn't really make any sense, but it's kind of interesting and looks sort of syntactically or from far away plausible. This is if you train your character recurrent neural network on Wikipedia, which has a lot of different kinds of facts, different links. You can read this. It's one thing that is amazing in some ways is that it actually can memorize words and a lot of different words, right? That is the first interesting part. Basically, this teaches us, and this actually comes back again when we look at images and sentences, it teaches us that recurrent neural networks can very well memorize pretty long sequences in their weights. What's the other interesting thing here is that it actually often correctly opens and closes parentheses. And that tells us something about the model, namely that it has memory and it can keep track of certain counts. It can keep track of having, here 2 different parentheses opened and then closed again later, which becomes even more important and impressive when you train it on LaTeX code. Here, however, there's one caveat, which is it didn't compile. And if you work in LaTeX, you know that maybe even for humans, it's hard to get your LaTeX sometimes to compile. So it was impossible for the algorithm to actually create perfect things. It would often say begin proof and then end lemma or something like that. So here it was actually manually fixed afterwards. But again, from afar, it sort of looks like a reasonable paper. If you have some really crappy conferences, you may submit it and get lucky. And the most interesting one in terms of the memory state was actually code trained on the Linux source code, which again from afar looks quite reasonable, and amazingly also opens and closes parentheses properly, even when there are lots of time steps in between. So why aren't we using those? Well, it turns out it doesn't necessarily give you the best semantic word vector representations that are then useful for downstream tasks. But what it does show is the amazing ability to actually have some kind of prior about what language looks like from afar. But of course, in the end, what we really care about is creating semantically meaningful content if we were to ever actually generate from a model. And in terms of the research, we're still very far away from trying to convey or trying to have a model generate not just locally syntactically plausible, but actually semantically meaningful sequences of text. So then this is one line of work by Tang Luang, who's a PhD student, and me and Chris Manning, and the slides here are actually from Tang, on going one level above that and not just assuming words are these atomic structures, but not going all the way down to characters either, but going somewhere in between, basically to the morpheme level. So having prefixes, stems, suffixes, and in some cases infixes. Though infixes are not very common in the English language. There's, pardon my language, very few of them. One is for instance, unfucking believable. So that is one of the few infixes that exist in the English language. So why do we look at morphology? Basically, we know that word vectors do very poorly when it comes to rare and complex words. So when you look, for instance, at different kinds of word vector computations and you look at distinct, what the nearest neighbors come out to be is not very ideal. So distinct here is different. So these look okay, but distinctness, which isn't a very common word in the English language, but we all know, what it means, basically gives us close to random nearest neighbors in the space. So this is again just looking at Euclidean distance in word vector space. The same is true for affect and unaffected. And so basically, the reason is that we treat, in many cases, the related words as completely independent entities. There's no connection between distinct, distinction, distinctive, distinctly, distinctions, distinctively, indistinct, and so on, right? They're all completely separate words, and we don't share any statistical strength between these different word vectors. However, we know that three of those are very, very frequent in the English language, and so we can probably compute very good word vectors on those three, and then try to do better by sharing some of the information between the word vectors. And now how do we do this? You will hopefully all remember this very simple model to train word vectors or to classify the center word in a window. This is our window-based model here again, where we just concatenate the 5 word vectors and have a standard neural network layer and in the end a linear output. Now, instead of training this to classify, for instance, whether this is a named entity recognition or to classify whether this is a reasonable window by itself with these words, what we can actually do is combine this idea with the recursive neural network that we also covered. And instead of assuming, unfortunately, it's just as one atomic entity, we can actually distill it or basically separate it into its prefix un, the stem fortunate, and the suffix ly, and then try to learn vectors for these and learn how to compose these vectors to form the full word vector. Basically, just two model ideas, two different model families that we covered in the class, combined with some linguistic intuition here that unfortunately has a strong connection to unfortunate, and that has a strong connection to fortunate. So once we do this, we actually get much better nearest neighbors, especially for rare words. And that is essentially the idea here. So if you really care about word vectors and the long tail of words that are not very frequent in your vocabulary, then you can either spend a large amount of time to try to get the largest possible corpus of the English language. So there's the Common Crawl, for instance, which is an attempt to have a snapshot of the entire internet, and that's what Jeffrey Pennington did for the glove vectors. but then even there you will have certain words that are just very infrequent. And with this kind of model, you could basically get away and still compute vectors for very infrequent words. Now, just one slide on the opposite spectrum and the opposite problem. What if you have very frequent word vectors, and the more frequent a word is, the more meanings it often has in the English language. So this is actually a paper by Eric Huang, me and Chris, on improving word representations in two ways. One, we actually allowed a global context where we average word vectors, as well as the local window context that we discussed in the class, as well as having multiple word prototypes. So we basically can cluster all the different contexts that the same word appears in, and then each cluster basically represents its own meaning. And so here, yeah, you can read this. For instance, you have jaguar, which is a type of instrument, as well as a car. Here, this is the Jaguar 1 meaning is close to luxury and convertible, so Jaguar car. And then you also have the Jaguar animal, which is close to hunter. Or you have the famous bank. Here you have the river bank or sandbank, which is close to plateau and canal. And here you have the money bank, which is close to finance, transaction, and laundering. So this also enables you to keep track over time, for instance, of different meanings and how different meanings shift over time. All right, now let's look at some more interesting and higher level tasks of NLP, namely natural language inference, which is a pretty hard task and requires in many ways a lot of knowledge about NLP and semantics, so we won't go into too many details, but basically it's a task that is very simple to define, but it actually engages us in the full complexity of various different kinds of semantic phenomena. And we'll go, for instance, and in the next slide, define lexical entailment here. And quantification is, for instance, saying for all men there exists a pet such that man likes that pet. So those are kinds of quantification statements in logic and logical inference. And some people, say that you really have to understand those kinds of statements in order to really have a good grasp of language. So here are some examples of training data where we then would like to see if we can A, memorize it, and B, generalize it to similar but different kinds of words. And again, here you can initialize these word vectors with GloVe and then see if you can train a model on top of them that generalizes. So in terms of lexical entailment, what kinds of options or relationships can there be between different words? And this is really just a short excursion into natural language inference and natural language understanding. So we know, for instance, that dancing entails moving. So whenever somebody's dancing, that means also that they are moving. Or, to waltz and tango, there's basically just a neutral relationship with them. You could be doing them almost at the same time, but it's unlikely. And in some cases, some words basically contradict themselves. You cannot be sleeping and dancing at the same time. So those are some of the different kinds of lexical relationships. And ideally, if we train this on dancing entails moving and waltzing entails dancing, then ideally the model would learn also that tango probably entails moving as well. Yep.
Are these the only three relationships? Or?
So it's a great question. Are there other relationships? There are actually these, but again, this is also in some ways an active research field, but people thought, and this is sort of the opposite of what we used to do in the rest of this class, right? We have some high level goal and we like to model to figure all these things out. Here we go a little bit into an intermediate step, and humans and linguists, and in this case Bill McCartney, who was also a PhD student with Chris Manning a couple years ago, is now teaching another class, 224U, this quarter, came up with a bunch of different potential relationships that two different sets can have. So you can have equivalence. So couch is basically synonymous with a sofa. You can have a forward entailment, saying a crow is a type of bird. And so here you basically have a little Venn diagram type thing where you say, all right, X forward entailed Y means that basically X is a subset of Y. You can have the reverse relationship, just European is the more general term, and French is a subset. You can have negation, having this symbol right here, basically an exhaustive inclusion. You can have all humans and non-humans, or all the things you can learn in Harvard Business School and all the things you cannot learn in Harvard Business School. You have alternation, so basically a non-exhaustive exclusion. Cats and dogs don't really span the set of all possible things in the world, nor the set of all animals, but they're definitely also completely exclusive, and you can either be a dog, X, or a cat. And so on. There are basically lots of different kinds of relationships. And what we want to do is we start with word vectors, but then ideally we can also go and actually predict logical truth statements for more complex phrases. So we start here with just single words. So jeans, pants, we basically want to predict that there's an entailment relationship here between these two words. So how do we do this? We basically have here a single word vector, another word vector, pipe them through a standard neural network. This could be a tensor kind of neural network where we have the multiplicative interactions that we covered in class 2, and we just have a softmax classifier on top of that. Very straightforward application of the kinds of techniques that we know, but applied to an interesting different data set. Yeah.
Where's the training data come from? And what is it?
So the training data here came from the student Sam Bowman, who worked on this project, and he basically manually created it. So manually / automatically. So you actually, from WordNet, for instance, you know all the things that are subset of other things, so you can very quickly generate tens of thousands of these kinds of examples. And then later on, you can create a grammar where you put your human knowledge into the grammar to create only valid kinds of entailment relationships. Now, the interesting part is when it comes to actually having recursion for longer kinds of statements. So basically here we train on relational statements that are generated from this formal system, basically just a grammar that instills the knowledge, and then we test on other such relational statements that we haven't seen at training time. But they're coming from the same kind of distribution that we generated. So here, the model will really need to learn not just the lexical relationships, but also the compositionality as we put multiple of them together. So for instance, A, it should be learned that it's basically equivalent to not A. There's a very, very simple example. Right? So in some ways, you would hope most humans who understand English would be able to understand if somebody's not sick, they're sick. And the way we can do this is, again, with the same recursive neural network type model that you implement in problem set 3, just this time trained on 2 pairs of trees. So we have one pair, one tree on the left side with a recursive neural network here, and we have another recursive neural network sharing the same weights on the other side, and then we just put them together into a single neural network layer and have a softmax classifier on top. So this is, again, here the beauty, right? You have different kinds of predictions, different kinds of data sets, but the models are very general and can be used for these different tasks. And that also goes back, actually, to the very first lecture of the class where we went over all these different models. And we basically, the main message there was it's the same model that can solve all these different kinds of tasks. And now that you go through them, you hopefully have a sense of like, oh yeah, I could implement that myself. How well does it work? Well, it turns out for some shorter kinds of expression, it actually works perfectly. And then even for very long expressions where you combine lots of different kinds of negation and entailment and combinations of those, even for longer expressions, if you have a large enough recursive neural network, which he calls tree RNN, you can basically do very well on this in 45-dimensional hidden representations. And of course, just summing up the word vectors and ignoring the recursive structure wouldn't do very well in such a complex logical task. All right, so that was another interesting application of these techniques. And we, however, might think, okay, well, this is still a synthetic data set, right? We didn't really use a real data set coming from real language. So here's one data set that I'm very excited about, and it's a very cool paper by Mohit Iyer and a bunch of collaborators from University of Maryland and me, which is basically a neural network for factoid question answering over paragraphs. So think of the Jeopardy IBM's Watson system, but think of it as what you would do if you were only a single PhD student and you still want to build a question answering system. So you don't have hundreds of millions of dollars of money, and you don't have a team of hundreds of people, and you want to build a question answering system. And hopefully, your first thought after this class is, well, I should use deep learning for this. And so here's an example of a training and a test pair. So the training input is basically this question. And this is this trivia competition. Quiz Bowl is actually something that runs nationwide in colleges. And I don't know, does anybody here know of? Are you competing in them sometimes? Oh, awesome. All right, all right, well, maybe you're excluded from the question, but does anybody know the answer to this question? James, do you? All right, very good. Thomas Mann. So basically, how do we train this? What does the model have to do in order to be able to answer those kinds of questions? Well, it turns out for every sentence in here, and again, or just for you to understand the hardness of the competition. So basically, after you can buzz in as soon as you know the answer, and it starts with more trivial facts and then becomes easier and easier as you go to the end, and by the very end you may say, all right, it's a German author, and these are the two most important books, Death in Venice and Magic Mountain, that he had written, right? So by the end it becomes easier and easier. And so when the algorithm will actually have to compete against humans, which they did run a real try in, Jordan Boyd-Graber, his advisor, and Mohit, and they're actually now at the national competitions, I think, in the next couple of weeks or so. They want to actually really have the algorithm compete Jeopardy style. Basically, the humans can buzz in as soon as they know it, right? And so as the algorithm, you also have to try to very quickly, from the first couple of sentences, know what the answer is. So how does this model work? Well, it turns out in the first version of it, they basically used a recursive neural network. And instead of here at the very top having just a single softmax layer, they used the inner product objective function that we covered in the class as well, and had a simple ranking loss that tries to have a large inner product with each sentence that describes a fact and a vector that represents a potential answer. So Thomas Mann, for instance, has a vector representation, and so do all the other authors that we know about. And then they just had basically the same the same max margin cost function, where you have now a potentially correct answer, C transposed with a sentence that actually describes a fact about that correct entity, plus some incorrect entity, let's call it I, transposed times that sentence. And you basically want the incorrect sentence vector, the incorrect fact that isn't, the sentence here that actually describes the correct thing, but with an incorrect entity, to be having a small inner product. Very simple objective function, just basically asks the model to backpropagate certain facts about certain entities through these inner products. What's interesting now is that as you train this model, it actually propagates now a bunch of facts about different entities, different individuals, or historic events, or countries, locations, and so on, from this kind of training objective into the entity vectors. And I say entity vectors because they actually pre-process it such that George and Washington aren't two separate vectors. They actually are one pre-processed phrase. And so here, George Washington, Thomas Jefferson, and John Adams, for instance, end up in the same part of the vector space. And this is, again, the vector spaces will usually be very high dimensional, like 100-dimensional or so. And we project it down into 2 dimensions here with PCA. And yeah, there are different kinds of applications, and here they zoomed in into one area of the space. But they also noticed that all the wars, rebellions, and battles, for instance, are in one part of the vector space. And US presidents here are in their own separate subspace, and there, early presidents are in, again, a subspace of that. Are there any questions about this model? Yeah.
Yeah, so we're doing our project on this topic. And
Cool.
when we're reading the paper, we noticed that at test time that you trained, I think, a logistic regression classifier instead of just using like the ranking loss.
Right. So I guess so there are two things. One, they have the ranking loss here for just the entities, but then they also eventually try to incorporate things like Wikipedia, because if you only train on the training data here, there are certain facts that you'll just never see. And so if you can train also on Wikipedia, then that improves your accuracy. But what was your question?
So is that why you need to use logistic regression?
Right. I'm sure there might be other reasons too. I mean, can't hurt. So the amazing thing is that despite him only being like one grad student with a couple of advisors and help, he is actually able to, for some of the sub-question types, actually outperform human players. So here, this is basically a history competition, and on the y-axis you have the score difference. So if your score difference is positive, then the model actually won against a person. And these are all actually legitimate quiz bowl players on the college level. And in history, the model actually can outperform in a majority of the cases people. However, on literature, that wasn't the case. So literature, people still won in 2/3 of the cases. And the main problem here is that in order to really be able to answer this kind of question, it's not enough to look only at the questions that you have in the training data. It's also not enough to just look at the Wikipedia entrance of that specific entity, because what you really have to do is read the actual books that those people have written, and then try to instill all the facts about those plot lines and not confuse those plot lines with the people themselves, right? So one, they don't have access to all those books, and so basically that was it's going to be a tough to win battle. Yeah.
Has anyone done that kind of work, like story modeling better?
Story modeling is hard. I don't think anybody has really tackled it. It's also, I guess, it's hard and there's not much money in it. So that is usually a bad combination. You need to have some very determined academics to push hard on that. It's also unclear what your objective functions are. So this one is nice because it actually has a clear, correct answer, but a lot of literature questions don't have concrete answers of like, oh, I understand literature because I got 79 accuracy. No, like literary scholars would laugh at you for that. So. All right, so let's move on to the last, and I think in some ways most recent and also one of the most exciting applications of deep learning and NLP, which is visual grounding, or essentially mapping between the meaning of language by itself and the meaning of images in our visual world into one joint space. So in some ways, we all are able to communicate in natural language, but we also learn a lot of the meaning of most of the words in language by interacting with the visual world. And so the first work in that space that uses deep learning on both sides is actually one of my papers from 2013, where we took a recursive neural network, same one that we described, but again on dependency trees, and we map that from all the word vectors, we map all the word vectors into one single vector that describes this phrase, and then we will train the model to try to predict a sentence vector that is actually close to a vector that we got from a deep learning model as well, but on the pixels of an image. And if that sentence, so a man wearing a helmet jumps on his bike near a beach, is basically visualizing or describing that image, then we want these two vectors to have a high inner product. So again, we'll use dependency trees. On the image side, we use a convolutional neural network. We only covered sort of the simplest models of CNNs for language. Really, CNNs, as some of you know, could be covered in entirely their own class and have been last quarter. Here we just used a simple convolutional neural network that was trained on ImageNet. I mean, simple in the sense that there's no novelty in it in the CNN literature, but it's still a very complex model. They're very large. It takes a very long time to train them on these large data sets like ImageNet. And then how do we train this? Well, it turns out it's exactly the same idea that we've had before here. We have basically correct pairs where we say this sentence is actually describing this image. So sentence I describes image J. And then we have a set of actually five of these sentences that describe the same image. And we basically select the correct sentence descriptions here. And then, the corrupt ones here, all the ones that aren't in the set that describe the correct sentence I. And then we just basically, again, maximize the inner product between pairs that are indeed describing the same thing and minimize the ones that aren't. Yeah.
Empirically speaking, what does the delta parameter have in terms of the results?
So the delta here is basically just the margin. It's a single number. Usually we set it just to 1. And so if it's 1, then every pair of sentence and images that actually show and describe the same thing should be having a larger inner product than any pair of a sentence and an image that aren't the same thing.
So when you're
up to this margin.
So say you're tuning for delta, based on some results you see, what's the correct decision what's one way to adjust the delta?
So the main way is just cross-validation. You try a couple of different ones, you look at your def set, and that's it. So again, this is an objective function that we've covered in class. We already know how to take derivatives with these inner products here. The one inner product basically just sends a delta into this recursive neural network, which you can also now implement. So in many ways, you could implement this yourself. There are a lot of open source packages like Caffe and others that give you a convolutional neural network pre-trained. So you could literally implement this model yourself with the knowledge that you have from this class and basically have images come in and be described. So let's look at some good results. So here we basically say for a given image, find us the sentences of a large set of potential sentence descriptions that basically describe this image. And here, because there are usually 5 correct ones, we can have up to 5 ones in green, and then red ones are ones that weren't correct. So they are not officially one of the 5 correct sentence descriptions of that image. So here you see, all right, in some cases, simple image does pretty well. Sometimes the second one is not actually, it's officially wrong in the evaluation, but it's not so bad. Young woman was riding a bay horse in a dirt riding ring. Could actually be correct, but it's actually officially the sentence describing a different image. Here, the first one was correct, and then a bunch of the other ones were wrong, and you can kind of understand why if you know a little bit about vision and what kinds of features these deep learning models are picking up. So white propeller plane, well, you have here something white that also looks like a white jet, and the propeller might be confused with the wheel, and so on. And this one is kind of interesting also. An elderly woman catches a ride on the back of the bicycle, which in some ways is ridiculous, but if you look at several n-grams, it's actually not so far off, right? So we have a lot of world knowledge knowing that elderly women are probably not doing those kinds of jumps on bikes, but it is a person, and could certainly be a woman, that catches a ride on the back of something that does somewhat look like a bicycle, but it's it's a motorcycle. So in terms of n-gram overlap, it's not so bad. What we basically find is that a lot of times these models do well in capturing the main objects in the scene, and if they've seen something in training that describes the overall scene well, then they do that correctly as well. But in general, there's still a lot of work to be done. So here we look basically at just the mean rank, how close is one of the 5 correct images ranked on average to the correct images and or text. And Now that I think of it, we actually have a fun demo of this too. So maybe I'll see if it's still up. Oops. Oh, it's over here. So here we do one direction where we basically we take a sentence, and in some cases just a word. We take the word vector that we have, we map it into vector space, and then we take just the pixels of the image, use a convolutional neural network, map it into the vector space with the convolutional neural network, and then find one from the other. And so this thing, just so you understand sort of how it's not magic, basically was trained on this data set where you have, for each image, you have 5 sentences describing that image. All right, so now for bird, and it's a single category, it's not so hard, but you can type in birds in plural and it actually pulls out pictures of that show multiple birds. So that's kind of interesting. It grounded the meaning of this vector space, which so far we've only trained on just language itself, in the visual world, and actually has some connections there. And what's more interesting is you can now say you can have birds on water, for instance, and it actually learns how these are composed to form the meaning of the whole scene. Or birds in trees. We'll try to pull up an image of a bird in a tree. And there are a bunch of other categories. And once you look at them, so horse, for instance, you can see here, and this is, again, it does not use this text. It just uses the pixels of the image. This is just to evaluate the proper sentences for evaluation. The relevance here is very high, so it's 15. If you look for an image or a category that this model has never seen, so for instance, zebra is not something the model has ever seen, I'll just do something random, but it also does that random with a very low relevance. So it actually kind of knows that it doesn't really know what this is. It just shows you the next closest thing. So if you say horse with bald man, for instance, it actually does pull out that one image with a bald man. It's kind of cute also that it makes mistakes where the images that it also thinks are close, actually people with helmets who maybe from afar look kind of like they're balding. But in general, this technology is interesting, and there are some interesting first steps, but it's certainly far from being working in a real environment as a real product. And that is in some ways even more true for going the other way, which is basically trying to describe images and not just pull out a sentence. So in the first work here, what we did was we mapped the sentences into vector space, we mapped the images into vector space, and then we found one from the other. But we couldn't really generate new sentences that didn't exist in the training data set, right? We could only find some that are matching. And so some follow-up work that actually came out almost at the same time late last year and for a conference this year, a bunch of different groups from different universities and different companies basically had the same model where they took some of these ideas, but they replaced their recursive neural network that just represents a sentence and actually used an LSTM to generate it. So in theory, they could describe completely new kinds of scenes. However, there's some post-hoc analysis later that was done and actually showed that really it just memorized a lot of the training sequences, and over 80% of all the examples that were generated for that particular image were really exactly phrases and sentences from the training data set. So it actually boils down to being a little more similar again to our earlier work, but in 20% of the cases actually generated new descriptions as well. And this is also an interesting, this idea of that they can memorize this is also similar to what we've seen with the sampling from the character recurrent neural networks, right? Because they also basically were able to memorize specific kinds of sequences locally. And so how do these work? Basically, they also use a convolutional neural network to get an image vector, and then they have this LSTM, which we also covered. And now the output, again, is just a softmax over all the words, and then they sample the description of the sentence. So there are a bunch of different groups that brought this out. Two prominent ones here from the Bay Area were Donahue from Berkeley and the group, the vision group at Berkeley. Their paper title is Long-Term Recurrent Convolutional Networks for Visual Recognition and Description. And then also here at Stanford, Andre and Feifei also had a paper on deep visual semantic alignments for generating image descriptions. And just to give you an idea of what these look like, here is one screenshot from the website, and it's kind of amazing when it works. So here you have, baseball players throwing a ball in game. Of course, you'd also know that there are very few images where a baseball player is throwing a ball and it's not in a game, right? Maybe he's just throwing it around for fun. And here you also see, some places where it really has a strong prior on the kinds of things that's seen in training data, like a young boy is holding a baseball bat, and you still see that it's lacking a lot. It's not like this is a solved problem, right? But it's definitely one of the most exciting research directions that really tries to ground the meaning of language and these semantic vector spaces in the visual world. Yeah.
So did both the models of like Donahue and Barkley, were both those models the ones where they kind of memorize sequences?
Right. Yeah. So there are a bunch of different groups. There are literally like 5 groups, and all in 1 week they all put out their papers on arXiv, and they basically all used a CNN on the image side, just like we did 2 years ago, and then had, I think, pretty much all of them in LSTM to generate sentences. So the models are really, really quite similar. It was sort of in the air. It's one of those typical, the kind of model idea was in the air for people to do. So in many ways, they suffer from the same issues. I think they would all create some examples where it works amazingly well, and there's just some minor problems. So this one, I don't think, is a woman. But then there are also a lot of them. So for instance, if you're in your training data, you train it with a bunch of white horses, and then on various different colored backgrounds, and then you ask for a black horse on a white background, it would still just basically generate white horse. Or you give it an image of a black horse, it would still say white horse on black background instead of vice versa, where you realize, okay, it hasn't quite fully understood which part here is black and white and where is the object and so on. But it's certainly amazing at finding enough correlation to be able to do it well in many cases. All right, well, that's it. I guess next week we'll have a lecture that actually won't have a video. So for those of you who watch it in time, I will talk about the potential future of deep learning for NLP with some not yet published results of one model that I think will solve most of the NLP tasks that we covered in this class. But it's all in the same model. So since unpublished, there won't be a video on it. All right, and that will also be the last lecture of the class. The week after, or maybe even next week, you'll have your poster presentation. Do prepare. The poster presentation is graded. Create nice posters. Ask us questions in the office hours if you're stuck or have questions about your posters. The simplest one you could do is just create a large PPT file, large PowerPoint file, and put it all in there. All right. See you next week.